Okay, so today's topic we'll start with the fourth unit, and we'll start with like FIR filters. FIR filters. By now we already know what do you mean by IIR and FIR, right? Again the same thing. You consider a LTI system, okay, x of n, and you have a y of n, and let's say this LTI system has got a impulse response of h of n. Now if this h of n is finite and this LTI system acts like a filter, then it is a FIR filter. So the first thing is it is finite in length. H of n exists for values from have got non-zero values from 0 to some value. Assume it's like a m. Okay, so this m is constant or finite. For this values from 0 to m it exists, for other values it is 0. Secondly, the LTI system acts like a filter, so that's why it is called as a FIR filter. Okay, so now coming back to the difference equation, we had a linear constant coefficient difference equation, right? Already taken, we had studied that constant coefficient difference equation, which was given as k equal to 0 to n ak y of n minus k equal to summation k equal to 0 to m bk x of n minus k. Now one thing we have to know is for a FIR filter there is no feedback coming in. Okay, so what happens here is there will be no delay elements with respect to the output. Okay, so here what you will have finally is for a FIR filter. For a IR filter this was fine. This was fine for a IR filter where there was a feedback involved, as well as there were like delayed components of your input too. For a FIR filter, what you will have is y of n will be equal to summation k equal to 0 to m bk x of n minus k. This is how it will be given. Think about a simple scenario. Let's say you have a LTI system. Okay, let's say there is a LTI system, you are applying a FIR LTI system or a finite impulse LTI response LTI system, where you are applying x of n and you are getting y of n. Now if you look at this, right, what exactly happens is since your h of n, let's say h of n is a finite, which is having a value of 1, 1 and 2. So its length is 3, where m is 2 now. M is 2. Okay, think about a system. This is finite, right? Finite. Okay, so what will be h of z? H of z will be equal to, given as summation n equal to 0 to infinity, or n equal to minus infinity to infinity, h of n z raised to minus n. But here it exists for n equal to 0 to 2, h of n z raised to minus n. So what happens here is this guy becomes z raised to minus 1 plus z raised to z raised to minus 0, 1 into z raised to minus 0 plus z raised to minus 1 plus 2 into z raised to minus 2. Okay, so what you get here is 1 plus z inverse plus 2 into z raised to minus 2. Now if I substitute this, y of z I know is equal to x of z into h of z. So what I get here is x of z into 1 plus z raised to minus 1 plus 2 into z raised to minus 2. Okay, so this is what I get, 2 into z raised to minus 2. So now if I take a inverse, this is like x of z plus x of z into z raised to minus 1 plus 2 into z raised to minus 2 into x of z. So what happens if I take a inverse Z transform? I get this y of n equal to x of n plus x of n minus 1 plus 2 into x of n minus 2. So this is of the form, see, there is no feedback happening here. There is, these are constant coefficients which are multiplied with the delayed elements of your input. Yeah. So this is basically your B case. This happens to be your, like, this is your B2, this is your B1 which is 1, this is your B0. Okay. So this is what you get, this is your B0, and the form looks something like this. This is your form where this is B0 into x of n plus B1 into x of n minus 1 plus B2 into x of n minus 2 plus it goes on till plus Bm into x of n minus m. This is what you get. Okay. So in terms of advantages, the FIR filter, they have a exact linear phase. Okay. We will come to that, what do we mean by linear phase. They have an exact linear phase, always stable because it's a bounded input, right. Then I mean it's got a h of n which is bounded, right. So design methods are linear, that's the third advantage. Advantages of a FIR filter is fewer number of side lobes in the stop band than an FIR filter with same number of parameters. The side lobes are in the stop band. I mean you have a filter response which is something like this. These ripples will be there. Okay, so these side lobes are fewer for a IR filter compared to a FIR filter. Okay, in the stop band. This is your stop band. This is your pass band. And the implementation involves fewer parameters, less memory requirements, and lower computational complexity. For IR filter, it is a lower computational complexity. So in cases, right, where you can allow a phase distortion, where phase distortion is not an issue, then you always prefer a IR filter because they are simpler to design. I mean, they have a lower computational complexity. Okay. If the phase, if linear phase requirement is a must, if linear phase requirement is a must, then you go for a FIR filter. Okay. Yeah. So what is, we'll come to now what is a linear phase and what do you mean by that. Okay. So let's, okay, yeah. So let's come to magnitude response and phase response first of all. Magnitude response and phase response. So magnitude response, let's say there is a h of n which is a impulse response of a FIR system or FIR filter which is finite in length. So h of e raised to j omega, which is the discrete time Fourier transform, is given as summation n equal to actually minus infinity to infinity h of n into e raised to minus j omega n. Now omega n. So now this guy here is finite and it exists for from 0 to m, okay, or 0 to m minus 1. So let's say this is existing from 0 to m, where m is the length. So what will happen here is summation n equal to 0 to m minus 1 h of n into e raised to minus j omega n. This is what you will get. Now here you have this guy can be written as magnitude of h of e raised to j omega, okay, h of e raised to j omega and into e raised to j some phase which is phi of omega. Okay, this is your phase, this is your phase, this is your magnitude. So this is basically a complex number, so you can express it in terms of polar plots. So now the magnitude m of omega is given as magnitude h of e raised to j omega, right, which is your real part of h of e raised to j omega. Okay, and okay, one second, square root of yeah, so square root of a real part of h of e raised to j omega the whole square plus imaginary part of h of e raised to j omega the whole square root of this. This is your magnitude response. The phase response is given as tan inverse of imaginary part of h of e raised to j omega upon real part of h of e raised to j omega. Okay, so this is your phase. Now for here I would like to introduce two more definitions, okay, which is phase delay and group delay. Phase delay is given as tau p, which is minus phi of omega, which is your phase, okay, phase response, divided by omega. Similarly, there is group delay, which is tau g, which is the derivative of the phase delay, derivative of the phase response upon d omega. Okay. So this is your group delay, this is your phase delay. Now for you to have for a system to have a linear phase response, linear phase response, right, your group delay and phase delay should be constant. Okay. So for a system to have linear phase response, okay, the tau p and tau g have to be constant. Okay, that means you should have it should not be dependent on omega. Okay, so this is a requirement for your system to have a linear phase response. This should be independent of the frequencies. Okay, so what it means is, let's say you have a LTI system and you apply some x of n and you get y of n. Now x of n will be made up of different frequencies, will be a combination of frequencies, right, combination of frequencies, and they will be passing through this LTI system and you will get y of n, which will be again some combination of frequencies. Now the frequencies, once it passes through the LTI system as a whole, it should be a constant delay, constant phase shift is what you should be getting. It should not be like one frequency is getting delayed by a amount x and another frequency is getting delayed by an amount another y. It should not be like something which is different for different frequencies. It should be constant. Okay, so that is what the significance of these terms are, the phase delay and the group delay. So all the frequencies as a bunch, they get delayed by a same amount. Individual frequencies also, they get delayed by the same amount. Okay, so now let's see what will be the for a phase response to be linear. You have phi of omega upon omega equal to some constant which is tau, where omega is from minus pi less than equal to omega less than equal to pi. Now phi of omega equal to minus omega tau. This is some constant which you assume, some constant. Okay. So I'm just looking at the requirement for you to have a linear phase. What should be the requirement? Okay. So this one phi of omega upon omega equal to minus tau. So phi of omega equal to minus omega tau. So I know that minus omega tau, phi of omega is tan inverse of imaginary part of h of e raised to j omega upon real part of h of e raised to j omega. This is what you have, minus omega tau. So what is imaginary part of h of e raised to j omega? I already know that h of n is this, right? So where I can write this as like summation n equal to minus infinity to infinity h of n into cos omega n minus summation n equal to minus. So I'll just pick this up, this guy here. Okay, let me just, yeah. So I know that h of e raised to j omega is summation n equal to minus infinity or n equal to 0 to m minus 1 h of n into e raised to minus j omega n, which is summation n equal to 0 to m minus 1 h of n into cos of omega n minus j summation n equal to 0 to m minus 1 h of n into sin omega n. Okay. So this is your real part, this is your imaginary part, this is known. So I can further factorize this as tan inverse of h of n. So this is a minus which comes out here. So this is a minus h of n sin omega n. So there is a summation sign here. So minus summation n equal to 0 to m minus 1 h of n sin omega n upon summation n equal to 0 to m minus 1 h of n into cos of omega n. So this is what I have. So what happens here is summation n equal to 0 to m minus 1 h of n into sin omega n becomes equal to summation n equal to 0 to m minus 1 h of n cos omega n into tan of omega tau. This is what I get. Okay. So this can be further expanded as summation n equal to 0 to m minus 1, where I write tan omega tau as sin omega tau upon cos omega tau. So what I'll get here is h of n sin omega n. This is written as sin omega tau upon cos omega tau. Cos omega tau I'll get on this side, so multiplied by cos of omega tau equal to summation n equal to 0 to m minus 1 h of n into cos omega n into sin omega tau. This is what I get. So further expanding, what I will get here is summation n equal to 0 to m minus 1 h of n into sin omega n cos omega tau minus cos omega n sin omega tau equal to 0. So this is like summation n equal to 0 to m minus 1 n equal to 0 to m minus 1 h of n into sin of omega n minus, or I can write this as omega n minus tau or omega tau minus omega n equal to 0. This is what I get. So what we have seen here is the solution to this particular equation, right? Solution to this particular equation is that if I expand this, so think about like if I put up some constant and expand this, the solution to this particular equation comes out to be tau should be equal to m minus 1 by 2. This will be the requirement. Okay, so that so now here if I plug it in here in this case, this is the first thing, tau should be equal to m minus 1 by 2 and h of n should be equal to h of m minus, so h of m minus 1 minus n, this for n from 0 to m minus 1. So these are the two requirements that you get. These are the two requirements that you get. This is the first one, this is the second one. So these are the two conditions for which this becomes equal to having a linear phase. The filter to have a linear phase. Now or you to have a constant phase delay or constant group delays. So these are the two requirements for having constant phase and group delay. So where you should have tau equal to m minus 1 by 2 and h of n should be equal to h of m minus 1 minus n. If you just need a constant group delay, then h of n should be equal to minus h of m minus 1 minus n. Okay, so this is basically a also called as anti-symmetric. This is called as a symmetric arrangement or symmetric filter. Okay, so there are two types of filters: symmetric FIR filter and anti-symmetric FIR filter. For a symmetric FIR filter, the phase delays and the group delays will be constant. Okay, if you need only the group delay to be constant, then it should be like h of n should be equal to minus h of m minus 1 minus n. Clear?